Okay, perfect. Okay, welcome everybody to another MCRN Colloquium. Today we're joined by Dr. Fatoumata Sanogo, who's an assistant professor at Bates College. Before that, she was a full-time lecturer at Smith College, and before that, she was working on her PhD at the University of Alabama, Birmingham, which she graduated in 2021. She has expertise in computational mathematics, image and video processing, machine learning, mathematical data science, multilinear and linear algebra, numerical analysis, and optimization. So a lot of great skills. So I'm very much looking forward to this talk today. And she'll be speaking about a spatio-temporal CP decomposition analysis of the New England region in the US. So with that, please take it away.
Thank you. Thank you for the introduction, and thank you for inviting me. So today I'm going to talk about a little bit about some data set that I recently came across. For this talk, I'll make mostly mention the motivation for this work, and then I'll have some data overview. Then I'll talk about the type of decomposition I'm using and show some numerical results. So we'll start with what got us into this, looking at this type of data. So we have an increased need of solutions such as developing more reliable predictive and diagnostic tools for weather and climate events, right, due to many natural disasters. So most of it is can be modeled via equations. You can solve them numerically using modeling equations, right? So in this case, we talked about numerical Earth system models, ESMs. The problem with these models is that they face two big challenges. One of them is heavy computational time, which limits the number of scenarios that we can have for exploration. And you also have the fact that due to the spatial resolution increase, you have a growth in the data dimensionality, right? So that can be solved many ways. And one of the most popular way, I would say, is using dimensionality reduction to do that. So dimensionality reduction is offer a better pathway to that, and most of the most popular one that I've seen a lot and that's been used a lot is principal component analysis, right? So it's the most popular tools that derive spatial and temporal representation. The only problem with that is that it treats variable independently, and it does also have some sort of orthogonality constraints that makes it really hard to have a clear physical interpretation of the decomposition or the components that we get, right? So that's what brought us to look at canonical polyadic decomposition, which is also called CP decomposition. So the good news about CP is that we can look at, we can do the dimensionality reduction looking at different variable at the same time together. And to do so, we look at something, we look at the multidimensional matrix, which is also called tensors, right? So in this case, the idea here is that for tensors, we are basically looking at a collections of elements that that has its own coordinate system. So basically, you think about tensors as multidimensional arrays or multidimensional matrices, right? So in this case, you can think about it a first order tensor to just be a vector. That's a 1D tensor. You have 1 columns. And if you think about a matrix, that will be a second order tensor where you have a rectangular shape. And a third order tensor where you have a third dimension will basically look like a cube. And a fourth will look like a columns of cube. And then you have a fifth that will be like a matrix of cube. And a sixth will be like a cube of cubes. I think that's where I stopped thinking about how to visualize it. But so that's the basic idea. And for this talk, I will focus mostly on the third order tensor. So which means I'll focus on the cube here. Right. So let's talk about the data set we are using here. So the data set that I have, so we looked at three type of variables or features in this data set. One of them is the total precipitation. The other one was the maximum temperature, and the last one was the minimum temperature. And we looked at daily values from January 1st, 1979 to December 31st, 2024. 2024, yes. So these variables, we just pick them because they are really important in hydrological studies type. So we wanted to use that and see what we can do with it. If there is a way to put them together, or it's easier to work on them separately. So the variable, the data is mostly, it's public and is viable. You can look at it at the NACODEX website. So here we looked at the model that used the Canadian regional climate model. Which is basically a way of running. Which was run under different scenarios forced by ARTIM. ARTIM is mostly the European model analysis. So we use the data with no interpolation, no bias, because we wanted to focus on the raw data for our analysis. So there was no interpolation or no bias correction here. So the data sets, the database actually on the website covers mostly the entire North America with grids from 340 cells in longitude and 300 cells in latitude. So we looked at the spatial resolution of 0.22 degrees, 50 kilometers. Right, so that was how we collected the data or downloaded the data from the website. And then what we did is we restricted the region, right? So we restricted the region to just New England. Actually, at first we restricted to the region of Quebec because my collaborator is from Quebec, but then we switched it to New England for this analysis specifically. So we did New England, which basically we looked at all of the 6 states, Maine, New Hampshire, Vermont, Massachusetts, Rhode Island, and Connecticut. Right, so that gave us like about 31 cells in longitude and 34 cells in latitude. So we had a total of grid cells in matrix of 1,054 grid cells. Right, so once we had the restriction done, then we looked at each variable we wanted to consider, which is precipitation, temperature minimum, and temperature maximum. And then we created the matrix of each one of them separately. So we had a matrix where we had 13,149 days in rows. And then in columns, the values were given looking at the grid cells, the locations, the grid cells that we created. So you had, this gave us a matrix of 1,349 by 1,054 for each variable. So X1 was in order, X1 is basically for precipitation, X2 for temperature minimum, and X3 was for temperature maximum. Right. So what we did here is that once we had all of the 3 matrices representing each variable together, each variable separately, we now put them together to create a tensor. So basically that gave us a 3rd dimensional tensor where we had all of the matrices sort of stacked together for all 3 primate variable. So that gave us that cube that I was talking about earlier. And then that was a tensor of 13,149 by 1,054 times 3, which represent the 3 variables, basically. So that's what we had. And sorry, I cannot see this Google Meet screen. What I have on my screen only is basically the presentation. So I don't know if there is any question. Maybe someone talk because I won't be able to see anything. I just wanted to mention that. So
Mhm.
So we have that, and then that was basically how we collected the data and how we prepped it. So once we were done with that, the next thing that happened is that because I was saying earlier that we, instead of using PCA, which is basically looking at the variable independently, we wanted to look at them together and see what we can do with it. I mean, and see if we get a better result with that. So for that to happen, we first looked at, we wanted to check actually if there is some sort of correlation between these variables in the first place, to sort of justify what's happening next, right? So we focus on each 4 continental seasons. So basically we broke it down, sorry, the variables into seasons: winter from December to January, and then spring from March to May. We did summer from June to August, and then fall from September to November. So once we had that, we looked at the Spearman correlation coefficient. But we did the correlation coefficient for the first thing is that we are looking at the spatial properties to see if there is some sort of correlation when we look at the geographic location. Basically, so we had to select a reference location to be able to compute the Spearman correlation. So for that one, what I did here is that for each one, you can see that I have the reference location as this little black square that I have on the bottom left. That's left, I hope. So on the bottom left right here, I have the reference location on each map. And what I have here is that the first column represents the precipitation correlation. The second column, that's for Tmax, and the third one, that's for Tmin. So temperature maximum and temperature minimum. And on the rows, the first row represents fall. The second one represents the winter. The third one is, what do you call it? Spring. And then the fourth one is summer. Right. So when we look at that, what we learn, as you can see on the graph here or on the map, most of the correlation were mostly positive here. They're all positive and mostly positive. And then more importantly, we also saw that the temperature minimum and the temperature maximum correlation have a pretty strong correlation all throughout, except maybe some pretty weak correlation around the up on the top for summer for Tmax and Tmin, temperature maximum and temperature minimum here. So in this case, we also have that the correlation for temperature maximum and temperature minimum are pretty similar for each season, with some a couple of differences in the winter and in the summer here. But the precipitation on its own has a pretty weak correlation all through all season. It's a pretty weak correlation here that we notice for precipitation on the spatial properties as well. So we also did the same thing looking at the temporal properties. So for this one, we looked at the autocorrelation function per season as well, at a given grid box, right? We also use the Spearman correlation. So we looked at same way, we looked at winter, spring, fall, and summer, right? And we did the autocorrelation function with lag expressing days, since we are looking at days for precipitation for temperature minimum and temperature maximum. Sorry, that's a typo, the ats, but the grid cell that we had is basically we look at the linear index, and then we just looked halfway through the flattened list of cells. So we flattened the list of cells and then looked at halfway through, and then that's the grid cell that we selected to compare to do our correlation for Spearman correlation here. So that gives us this here. right? So again, like in the spatial correlation, in the temporal as well, we can see that we have very strong ones when it comes to temperature minimum. Sorry, by the way, I have to say that. The first column is for precipitation again, the second column is temperature maximum, and the third column is temperature minimum. Right. So when we look at the temperature maximum and the temperature minimum, again, the correlation was pretty strong, except maybe in laters. Sorry, in this case, we were looking at only 30 days. I did the plot only for 30 days, but if you look at the rest, it's about the same similar trends. And also for later days in in the summer, sorry, fall. The first row is fall, the second row is winter again, and the third row is spring, and then the fourth is summer. So if we look at the fall row for temperature maximum, we see that we have a correlation. When we look at the later days, it's pretty weak. It's a little not so strong. But then in the winter, it's pretty strong and so on. So we have overall a stronger correlation when we are looking at temperature maximum and temperature minimum. But for precipitation, on the other hand, like the the spatial correlation here, the spatial correlation, the correlation on the geographic, it's basically about the same thing for the temporal as well. It actually looks like it's weaker on the temporal correlation. It's much weaker than for the, what do you call it, for the geographic one, sorry. Okay. So that was how we did a little bit of data exploration based on the correlation between the variables. And then I have that. So now I will move to what's kind of dimensionality reduction analysis we did, which was based on canonical polyadic decomposition, right? Any questions so far?
Yeah.
Yes.
So sorry, this is definitely not my field, but these 30-day plots in your temporal properties, these are 30 days from the start of the seasonal window. Is that correct?
Yes.
Like, okay. Do you think that if you, because each of the windows is what, about 2 months long or so?
Mm-hmm.
Do you think you would have had
Mhm.
symmetry in some of these plots if you'd gone out for the full window?
Maybe, I don't know, because I haven't looked at the full window. It was much harder to be able to plot the entire thing. Since I have like more than 13,000 days to look at,
Okay,
right?
yeah,
So
that's fair.
yeah, so I tried to only look at those 30 days, and then I looked at another 30 days window and another 30 days windows. I just looked at a bunch of plots with 30-day windows every time and see if I'm seeing the same, not necessarily the same exact pattern, but if I'm seeing the same kind of conclusion where the correlation was stronger for temperature maximum and temperature minimum, but for precipitation, it was weaker. And that definitely for each window I was looking at, the correlation was much weaker on for precipitation. It was much weaker on all of the windows that I was
Yeah,
looking at. Um,
okay.
I don't know if
And
that answers your question. Yeah.
I think so. Yeah. I had another question on the spatial slide.
Yes. Okay.
And again, yeah, definitely not my field. But so if I'm understanding correctly, so this is correlation of spatial location with whatever variable corresponds to the column. Do you why the like sort of patterned striping of low and high correlation that you're starting to see in like the lower right hand side? Do you have
The lower right side.
Yeah, so like lower right hand side, so that's what? That's winter is the fourth row or
No, winter is the second row.
okay, so whatever season that is,
Mhm.
and then that's minimum temperature. You're just seeing this like striping pattern happening where you have areas of high correlation and areas of low correlation spatially with the minimum temperature. I was just curious, is that like an artifact of the method, or do you have any idea what's going on there?
That was actually very surprising when I saw it, because I actually, if I can, I don't know if I can pull that up quickly, but I actually tried it with other locations as well. And because I was also thinking maybe it was an artifact or something when I saw it the first time. So I actually tried it with other location, and I had about the same kind of artifact. Not exactly the same, but I do have some sort of artifact here. So that is something I'm still thinking about why exactly that happened.
Interesting. Okay.
Yeah, because I tried it also with that, and it did the same thing to me. Sorry.
Okay.
Yeah. So I'm definitely open to knowing more about why this is happening.
Yeah. Okay, cool. Thank you.
Yeah. Any other questions? Okay. So let me look at now what I did next. So in this case, what I try to do now is go to the dimensionality reduction idea. And so I tried the canonical polyadic decomposition. So for the canonical polyadic decomposition, we want to look at, we have a third order tensor. The way it's going to work is that if I have a third order tensor, I can break it apart into 3 factor matrices. So it's similar to SVD, singular value decomposition, where in singular value decomposition, if I want to look at it into the dimension side, I'm basically breaking it apart into 2 vectors. So I have a sum of the column of vector u, if you divide it by as a matrix u times some diagonal matrix with the singular vectors, and then a matrix v transpose. Then you basically have a column, a sum of the vectors of column of U, and then the rows of vector V, matrix V, sorry, right? So it's the same idea here, except because we are in the 3rd dimension, you have this 3rd dimension that adds to it. So you find yourself with a 3D basically vector, which is a 3D outer product, which represents a product of those 3 vectors. And that's what you will call a rank 1 tensor, basically, because in this case, I'm looking at 1 vector in each dimension. And then I'm looking at the outer product. Visually, that would be represented by this, right? So I have that, and then so I looked at the canonical polyadic decomposition now. So if you want to do that now for the entire space, or basically the entire rank that you're looking at, so like the principal component analysis, you can choose the number of components, or in this case, the rank, basically, what rank you want. So in our case, we wanted to take the smallest possible rank and see what we get, because the smaller the rank, the lower the dimension. So we were looking at, in this case, so I have the first factor matrix. So these are called the factor matrices. And that's basically how the CP does. It would break it apart into sum of rank 1 tensors. And then each rank 1, for instance, if I'm looking at this column A1, all of the column of A1 all the way to AR will represent my first factor matrices A, and all of the vector AB1 times all the way to BR will represent my second factor matrices. And then you have all of the C1 all the way to CR will represent my third factor matrix, right? And then basically I'll go all the way to R, because that's where R is basically how much you want to go. How many components do you want to generate? Or what's the rank of the decomposition you want to generate, basically. And this sigma here is just the rescaling coefficient. It really depends because some people do not use sigma. They do not take it out. It's basically, think about it as like a weight or something. So it doesn't, they don't really take it out. Some just blend it in the decomposition. So which means instead of having sigma, you can have the sum of A out of product B out of product C. Or you can pull it up if it's something you actually need for your decomposition. In my case here, I actually did not pull out sigma. I've just took my factor matrices because these are the ones I needed to be able to do my decomposition and to be able to have my interpretation. I didn't really have any need for sigma, so I did not care about it. I just blended it in my factor matrices. So in my case, sigma is not there. And more importantly, so in the decomposition that I showed, I mean, in the matrix that we are using, if you recall, you have the time, which are the days, and then you have the, what do you call it, the location, which is on the rows. So it's basically time by location by the number of variables that gives you the tensor, right? So in this case, what that tells us is that the first factor matrices, which is going to be the time by the rank, which in this case, the days by the rank, is going to represent the temporal modes, so the temporal matrix. So that will represent basically the temporal modes of your data. And then the B will represent the spatial. So that will consider the location. If that will be the spatial, I mean, the location mode, the geographical mode. I cannot pronounce spatial, so I just keep using geographical. And then you have C, so that will be the variable. I mean, it represent basically, if you want to think about it as the number of variable we are looking at. So that's the variable modes, the future modes. So that one, for instance, in my analysis, I didn't really care about C because it didn't have anything that I wanted to look at. Mostly, I wanted to look at the spatial mode or the geographical mode or location mode, and then the temporal mode. So these were the two modes that I was interested in. And I focused only on A and B when after I did the CP decomposition. I didn't really use C because it wasn't useful for the analysis as well. Okay, so to do CP, so that's when also the change starts. So to do CP decomposition, we have basically we used alternating least square analysis approach, right? So that's what I used in this case, the alternating least square approach. So what happened for alternating least square is basically, well, if I want to do a dimensionality reduction or any dimensionality reduction, I just want to minimize my loss function, which is the difference between whatever reconstructing matrix or tensor I have minus and the original tensor, right? And then I'm trying to minimize the norm of that. I mean, the square norm of that. So in this case, if you want to minimize that, you are basically going to do what do you call it? You're going to take the gradients of that loss function, right? So ALS basically what I do here is that in this case we have 3 factor matrices to find. So we fix the other 2, and then we find one of them, and then we go again, fix the other 2, and then we find the other one, and so on until we find all of them, right? Until you find all of the 3 factor matrices. So ALS is the most popular way to go about finding the CP factor, right? The only thing with that is that it's very simple, but the only thing with that is that it has some issues. For instance, it doesn't have anything about it hasn't been well developed when it comes to spatio-temporal data, which I think it is important, which I will explain soon. And then also, when you have a noisy kind of data or non-orthogonal or very high rank, then it also has issues with that as well. The algorithm does have issues with that by the convergence might not, you will have many local minimum, basically, especially if you have the signal to noise ratio not sufficiently strong enough or large enough. Then it will make the convergence to the true loading vectors not so certain, basically. So that's what ALS does. So what we decide to do here instead is still use. So the idea is that to solve that issue, there's a lot of literatures that focus on the initialization step. So because ALS start with I'm fixing one, and then I'm fixing two, and I'm solving for one, and I'm fixing two, and I'm solving for another one, you somehow have to feed the algorithm some initial factor matrices to start with, right? So for that, initialization is pretty crucial. The way it is being initialized will help solve these problems that I mentioned earlier. So the most popular initialization method, like I said, there's a lot of literature on that, is basically the higher order singular value decomposition. Like the name explains, it's basically singular value decomposition, but for multidimensional matrices. And then you also have a randomly generated vector. So the idea is that you're going to take that tensor that you're trying to find its CP decomposition of, and then find the singular value the higher order singular value decomposition of it, and use that to create your 3-factor matrices that you need for your CP decomposition, feed that to the algorithm, and use ALS now to solve it. Right. So, or like another popular way of doing it is basically ask the computer to randomly generate 3-factor matrices for you, just randomly, and then feed it to the algorithm and solving through ALS. Right. So higher order singular value decomposition literature, from literature, we know that it did really well, especially but for when you choose the number of components to be 1. So when you're looking at the rank to be 1. Otherwise, when you increase the rank, then it has issues in terms of finding the true loading vectors. So here we propose a technique that will focus on the spatio-temporal property of our data, right? So instead of using just higher order singular value decomposition, which is basically pretty much works for anyone, we want to specifically focus on the fact that our data is a spatio-temporal type of data. So in this case, we did that by using the spatio-temporal principal component analysis. Okay, so here, the principal component analysis that we use can be, the principal component analysis is basically performed how? We look at the sample covariance matrix, and then which is centered of the centered data, and then we found the eigenvectors and eigenvalue of that covariance matrix. And then those eigenvectors will be your principal components, basically, right? However, this approach does not take into consideration the time dependence, which means nearby location, the geographic dependence of your data as well. So no time dependence is taken into consideration, or geographical dependence is not taken into consideration as well. So you also have something called the spatio-temporal principal component analysis. So this one considers both of them. It's basically a functional time series kind of analysis. So the idea is basically what? So what the spatio-temporal principal component analysis does, so STPCA, you generate a list of matrices. So in my case, I generated a list of matrices earlier. If you remember, we did like a matrix of the precipitation, a matrix of the temperature minimum, and a matrix of the temperature maximum, right? And then with that, once I had that list, the data matrix is now, this list of matrices will be transformed into a multivariate functional data sets, right? So the transformation is done basically by using Fourier transform. So we will use Fourier transform to create a matrix called A, and that matrix will be of size, in this case, the number of days, times the P is the number of variable, and K is the number of bases you decide to have on your Fourier transform, right? So if I decide, in my case, I choose 25, but you could decide 24. It really depends on your data set. So after that, once you have the data transformed that way, so this is basically sort of doing like a periodic transformation. So in this case, this transformation takes into consideration the time dependency of your data. And now for the location dependency, what we did here is that we found the pairwise distance between each grid cell. So remember, we created a grid cell of the latitude and the longitude coordinates. So we look at all of each coordinate and then find the pairwise distance between each coordinate. And then once we had that, we used that to find the spatial weight. So we created a matrix a weight matrix basically with that, and then link that weight matrix to the matrix that we created earlier, A, through a projection basically. So we are basically projecting that matrix A onto the functional space that was created earlier. So that gave us, so once we had that projection, which created a spatial correlation matrix, all we did at the end here is that we, this matrix was now, we now found the eigenvalues of these matrices and then the associated eigenvector of these matrices. And these eigenvectors became now the spatio-temporal principal component analysis here. So the only downside about this is that your method is the principal component you're going to find is entirely dependent on what spatial weights, how you're going to compute your spatial weights, basically. Because when you use the pairwise distance, you can use many ways to find it. In my case, I use the radial distance weight, but you could use even the nearest neighbor distance weight. There are many options. So depending on which one you are going to use, those components will change. And more importantly, unlike the regular CPA, these ones, the eigenvalues can be positive or negative, because you're not looking at the regular covariance matrix anymore. But in this case, you're looking at the spatial correlation matrix. So in this case, so we had that. So I used the spatio-temporal principal component analysis. And then I used that to initialize my factor matrices, if you recall, the initial factor for my ALS algorithm. So basically, once I had that, those components, I created 3 factor matrices from them, and then used that into the ALS algorithm to to find my CP decompositions values, my CP factor matrices. And then I compared it to the most popular ways of initializing our data, which is basically our matrices to find CP, so which is higher order SVD and random idea. So I put all of that together in MATLAB, and then this is what I had at the end. Basically, when I did the initialization with higher order SVT, when I choose the number of components to only be 2, these were the relative errors that I got. And then when I choose the number of components to be 3, these were the relative errors that I got. So the relative errors, I just did the regular one that we usually do, where you have your estimate minus your true divided by your true. So that's exactly what I did here. And in this case, every time I did it, the one with initializing with the spatio-temporal principal component analysis had a better relative error compared to the others, the other kind of decomposition. But definitely higher order SVD did trump the randomized idea. But also I also looked at something else, because in climate analysis, sometimes to do anomaly studies, we want to be able to group our data somehow. And usually we use clustering to do that. After dimensionality reduction, you want to use clustering to sort of group your data. So that was my next step. So I looked at the clustering, but using each of these factor matrices that I found from all three initialization process. So I basically did k-means. I use k-means. And then the way I did k-means is that for CPD factor with initialization method, so I used all of the initialization method. But like I said earlier, I use only two modes, the temporal mode and the spatial mode to do KNN. Like I said, the third mode wasn't really important in this analysis, since I was only looking at the temporal and the spatial mode for my data. And I use this silhouette score to check how well separated my data were. So the silhouette score is basically the average of the intra-cluster distance and the near cluster distance. So in this case, you're looking at the distance of a component to all the other components within the same cluster, and then the distance of the component to the nearest clusters, basically. So you're looking at the average. So that's the silhouette score. So I did that for when its rank is 2, so which means 2 components. And then when I was looking at the temporal mode, these were the silhouette score for each one of them. And the one for temporal, ST, using the initialization method of spatio-temporal principal component analysis, this matched better again than the other one. And then also for the silhouette score, the best case that it picked is different than for the other two. It picked the best number of clusters to be 4, while the other picked the best number of clusters to be 2. And the silhouette score was a bit higher than the other one as well. So I also tried it with when the components were 3 as well. And then I also had about also different cluster here. The cluster number for the other two type of initialization gave me 3 and 3. But for STPCA, I got 2, and then the silhouette score was much higher. So the silhouette score basically is considered good the closer it gets to 1, basically. And then here, the best K, I found 2 every time, but the silhouette score was different. And it wasn't so different with the random and the STPCA. There weren't that much of a difference, but that's what I did here for all of them. And then I got there. So from there, I concluded my analysis, at least this parts of the analysis that I wanted to talk about today. And so in this case, to summarize, basically what we did is that we used the spatio-temporal principal component analysis to initialize our CP factors, and then applied that to our data to see how good of a cluster we are going to get for our next studies, which is basically about anomaly studies. But for future work, we want to see if we can integrate that maybe into a deep learning architecture, but mostly look at anomaly studies also, and if we can find a much more robust spatio-temporal tensor decomposition. That's not necessarily initializing the CP factors. That's where I will stop, and these are the references that I use. And the paper is also on the archive if you want to go over it. But thank you.
Awesome. Thank you so much. That was a very interesting talk. Let me find my clapping emoji. There we go. Okay, we have some time for questions. If anybody has any, please go ahead.
I have a quick question. The data that you use. I mean, so can you
Mhm.
talk about the different? I'm thinking it's like it has more than one dimension to it, right? So can you talk about the different components of your data that you use to do your analysis here?
Or like the different variables that I used, or
Yeah, yeah, that's right.
yeah. So when I downloaded it from the website, I had to take each variable separately. So I looked at the precipitation variable and the temperature minimum variable and the temperature maximum variable. So that created three different file of data. And what I did from there is, after restricting it to the New England region only, then I created a matrix, which was basically a matrix of time by location. So the columns were representing the grid cells for each location, and then the rows were representing each day. So I was looking at it daily instead of monthly or anything like that. So that made time by location. And then what I did next is basically putting them together, basically stacking them to create like a cube. So mostly it's 3 dimension, I mean, create a third dimension basically, which will be the number of matrices that I'm adding together. So in this case, I did precipitation, and then I added temperature maximum to it, and then I added temperature minimum in that order.
So then
Um,
you're looking at
mhm.
you're looking at New England, and you kind of looking at the spatial map, right? So how fine is your grid?
How far is my grid?
How fine? How fine? Do you did it like big grids or small grids, or how to get the data set that you did?
Um, Actually, the coordinates matrix is provided on the website as well. So I
Okay,
didn't create the grids. I mean, sorry, I didn't create like the grid. The location, latitude and longitude are already provided from the website. So you just have to sort of like find the location that you're looking for by providing your own latitude, minimum latitude and minimum longitude, and then you can find the grid cells. But the grid cells are already provided from the database. I don't know if that's what you were asking.
that's correct. Okay,
Yeah. Mm-hmm.
well, thank you.
No problem. Thank you.
Okay. Any other questions? If not, I have one. Could you pull up that figure with the correlations again? With the
Which one? This?
it
Okay.
was, yeah, it was very near the beginning, I think.
This
Yes.
one? Okay.
Yeah, I'm just wondering. I was curious. I was looking at a topographic map.
Mm-hmm.
With the correlations. The bottom row was summer, right? I think.
Mm-hmm. Yes.
So in the summer, it almost looks like the sort of negative correlations. It's just to make sure I understand. It's also the correlation with where the black box is, right? With that location.
The location, yeah,
Yeah.
the where the black box is, yeah. We have found the correlation using the black box as a reference, yeah.
Okay. Okay.
As a reference location. So the black box is the reference location that I use to do the spatial correlation, basically, like the geographical correlation. So every other location were compared to the black box location.
Okay. Okay.
Yeah.
It's just looking at a topographic map that in the
Mhm.
summer, the blue areas, the negative correlation, at least over Maine, kind of, I think it corresponds to where there's like the sound. What is the name of that sound? But around Newfoundland, and then there's like, I guess a delta going into Montreal above it. But I almost wonder if it's related to the water there somehow.
That's showing like the weak correlation.
Yeah, because it would
Mhm.
well, I guess one is not negative, but yeah, weak correlation. I guess, well, I don't know maybe why you wouldn't see it in the winter too. But I mean, one is land and then one is a lot closer to water, and you have a lot
Mhm.
more influence from the ocean maybe in that location. So it might not correlate as well to that point, if I'm
Mhm.
understanding it right. Anyway, just was trying to trying to figure it out, but
Oh yeah, I'm more curious about that too because I had the same thing. But I also noticed that when you are doing like the correlation are stronger when you are closer to that reference location.
right,
At the
of course.
further you get away from it, the correlation are a little more weaker as you get far away from the reference location. So I'm also thinking about the fact that maybe the reference location is also might be influencing what's happening here.
Right, I see. That makes sense. Yeah. Okay.
Yeah.
Yeah, and somehow just stronger or more of an effect in the summer. Okay, cool.
Yeah.
Let's see. Okay, any other questions?
Yeah, I guess just like a general question. So for a lot of this talk, I think the idea was developing your method. And I used to hate it when people would ask me this question in math talks, so I apologize now for asking. But at the end, if you had to like kind of give a takeaway for the original physical system that you were looking at,
Mhm.
what is the takeaway?
For the original system, like the data set I was looking at, or the
Yeah,
method,
yeah, the
like
data set that you were looking at.
um, so I would say for the data set I was looking at, was mostly looking at how it would do if I tried to register dimension, how well it could do and not. So I haven't really thought about in terms of how the reduction will conclude in the data set, actually.
Okay.
Because to be honest, I was more focused on the method
Yeah, no,
and
I
seeing.
understand.
Yeah, I was more focused on the method, but like I said, we are still exploring the data because I want to know more about, especially the correlation analysis. I think there is more to look into there to have a better conclusion about what's happening with the data. I think even if the method is proving to have some good result, I still need to look more into the data set to see how that could actually help with the rest of the analysis or the data set.
Yeah, and I was wondering if there was something, and maybe you said this and I missed it, but if there's something about that was about this data that made you want to use this method, like something that you weren't able to figure out about this data using maybe just like a traditional principal components analysis that led you to use this method to try and develop this method using this data in particular.
Oh, that's a good question. So I started with actually trying to do a downscaling analysis. So if you're familiar with that, that's basically where you have like, think about it as I have a big map, and then I'm using maybe a magnifying glass and somewhere on that world map, and I want to see I want to get some specific more specificity about that specific location I'm looking at, but using the overall map. So downscaling is basically trying to have a high resolution on a specific location when you have a low resolution, basically a broader surface. So that's what I was trying to do. And then, like I was saying earlier, the problem with this kind of analysis and the fact that we now have so much data, it was the issue. And then we did it with actually PCA. But we were wondering if we could act, because we know these three variables we were looking at is really important in hydrological studies. So if we could actually look at all of the variables together and we have a better answer when it comes to dimensionality reduction, we're thinking maybe that will help us with the downscaling analysis. But also our final goal was to do some kind of cyclone analysis, so extreme weather prediction. So that's basically the final goal, but we wanted to start first with finding a good idea or a good way about the dimensionality reduction first before we move to those analysis, those other things. So that was the reason why I got here.
Okay.
Like you
Very
start
cool.
somewhere and somehow something else come up.
Yeah, you end up somewhere totally different. Yeah.
Yeah.
Awesome. Thank you.
Okay. Any other questions for Fatu? Okay. If not, then hit the clapping emojis again, of course. And thank you so much. It was really
Thank
interesting.
you.
Cool to see these, new methods developed to help deal with these huge, climate data sets, because it's definitely a big task. So, okay. So yeah, with that, thank you again, and we should see you all next week.
Thank you.
Bye, everyone.
Thank you, Fatu.
Bye.